Hi there. We continue today with this video, which is about pyruvate dehydrogenase, the gateway reaction to the TCA cycle. So let's get to it. So what's the reaction? Again, from pyruvate, we're going to make acetyl-CoA. And it is acetyl-CoA that actually will get into the TCA cycle. So this reaction really links glycolysis, which makes pyruvate, to the inner mitochondrial processes of the TCA cycle that really get fed acetyl-CoA. Okay, that's the carbon that enters the TCA cycle is acetyl-CoA. So the two carbons. So this is pyruvate. This is coenzyme A, CoA. And what we're going to see is that two carbons from acetyl-CoA, so this carbon and this carbon, these two, will find themselves onto the sulfhydryl group of coenzyme A to give acetyl-CoA. So, and this carboxyl group of pyruvate will be converted to CO2. So you see it here. And it's a redox reaction because the oxidation state of this carbonyl, carbon here, okay, will change. This carbonyl will become a thioester, so an ester. So it will be equivalent to a carboxyl carbon. Okay, so this carbon will get oxidized, which means some electrons will be lost and be transferred onto NAD plus eventually, not right away, as you'll see, to become NADH. And that also will be used to feed the electron transport chain, as we'll see. We counted in the general tally of NADH molecules that will be generated. All right, so the problem is, yes, this reaction links, as I said, glycolysis, which makes pyruvate, with the TCA cycle, which starts with TCA, with acetyl-CoA. The TCA cycle and pyruvate dehydrogenase are found in the matrix deep inside mitochondria, in the mitochondrial matrix. Pyruvate, as we saw from glycolysis, all of glycolysis is happening in the cytoplasm. So somehow pyruvate has to come into the matrix of the mitochondria. And the inner membrane of the mitochondria is so tight, it's impenetrable to anything, including protons. I mean, that's the whole point of the electron transport chain and finally to make ATP. So how does it come in, right? I mean, this is a big problem, even though Krebs got his Nobel Prize in the early 1950s and discovered all these things, the TCA cycle, in the 1930s. It was a complete mystery how pyruvate actually makes it into the mitochondria to kickstart the whole process. And finally, that was solved only a few years ago, right? So just to show you how many fundamental things just linger for decades and decades. So in 2012, in a major paper in the prestigious journal Science, this group from the University of Utah discovered that there is an actual transporter that's specific for pyruvate, and it's got multiple subunits, MPC1 and MPC2. So the MPC complex makes a transporter which brings pyruvate into the inner mitochondrial space in the matrix. There is a transporter, okay? And in fact, it's important because if you don't have it, so this import, how important is that import for the whole thing? I mean, I keep telling you that this is what you use to link glycolysis with the TCA cycle. Well, if you don't have that, you don't have that option. So pyruvate will will have a different fate. And we've seen that fate. Pyruvate, in the absence of the TCA cycle and oxidative phosphorylation, will become lactate, right? It will go into fermentation, it will be a substrate for fermentation. And in fact, in children that have mutations in that transport that cannot properly import pyruvate into mitochondria, they suffer from various things, including lactic acidosis, which is the buildup of lactate, because that's what they generate from too much pyruvate, because pyruvate has no other way to be consumed. All right. So problem solved, and let's get back to the enzymology. Again, this is where it's going to be the acetyl group. So what is that enzyme? It's a reaction that breaks carbon-carbon bonds. Which bond is broken again? It's this bond right here, okay? The one that connects the two carbons, the carboxyl carbon and the carbonyl carbon on pyruvate. We have seen that already. In fact, we have seen a pyruvate decarboxylase in the alcoholic fermentation, where in yeast, where you get acetaldehyde. So parts of the mechanism are actually very similar. We're going to see how it gets decarboxylated. And this one is a little special because it's actually it belongs to a different class called oxidative decarboxylation of alpha keto acids. That's an alpha keto acid. That's the alpha keto group here. So just to go through some color scheme, and we'll do the reaction in detail on the board. But this is pyruvate again with the oxidation states of its carbon. This is the carboxyl carbon, so it's the most oxidized. That's red. That's the carbonyl carbon, the alpha keto carbon. So that's yellow. And this is the methyl group, so it's in the hydrocarbon, the most reduced state. So as I said, with a reaction, the carboxyl carbon will leave in the form of CO2. Okay. Now this carbon gets oxidized. It becomes red, from yellow to red. So it becomes the equivalent. It becomes a thioester, but that's the equivalent of a carboxyl carbon at the oxidation state. The two electrons will, because that's an oxidation reaction, they will reduce NAD plus to become eventually to become NADH. Right? So that's the acetyl group. Okay. Now, so it's these two carbons became the acetyl group. That's an acetyl CoA. I highlight them in in the gray background to indicate in future reactions their source. This is the source of carbon that comes into the TCA cycle. And the star here, because it's actually a high energy bond here, it's a thioester bond. So it's an activated two carbon unit. It's an extremely thermodynamically favorable reaction. It's got a delta G of minus 33.4 kilojoules per mole. So that's very substantial. Okay. It's practically reversible, right? The complex, the enzyme is a giant. It actually has three distinct parts. Part 1, E1, then E2, and then E3. So pyruvate decarboxylation happens by the first catalytic activity, the E1 enzyme. Then the acetyl group actually, before it gets onto coenzyme A, we'll see it moves onto lipoic acid. That's a new core factor we have not seen before. We'll see how important that is. And then from the E2, it will get onto the coenzyme A, okay? And the E3, so at that point we're done, okay? We have actually decarboxylated, so we made CO2. We have made acetyl-CoA, right, straight from the first reaction. So the E3 now, however, we have not seen NADH yet. We have not seen where do the electrons end up. The electrons from the oxidation of this carbonyl, they reduce this lipoic acid. Okay, but that's not the end product. And for the reaction to keep going, we have to reoxidize lipoic acid, and you'll see how that works. And that's the job of enzyme E3. Okay, so for multiple turnovers, you absolutely need the E3 enzyme that will eventually, take the electrons from lipoic acid and put them onto NAD plus to make NADH, and in that sense, it regenerates the oxidized form of lipoic acid, so the reaction can keep going. So it's a huge complex. It's 5 nanometers in diameter, the whole thing. It takes up about 5% of the diameter of a cell, of a bacterial cell in this case. So it's huge. Just the E2 part has like 60 subunits, and it looks beautiful. It's like this. So it's a complex reaction, okay, no question about it. So how does that happen? So we've seen this before for every decarboxylation. Okay, so this is a carboxyl group. To decarboxylate that and release CO2, this is not trivial. And the reason that it's not trivial is because when you do that, and this R group will have a carbon, you will generate a carbanion, and the carbanion has to be stabilized. They're very unstable, so that's what's slow. So whatever facilitates the stabilization of the carbanion will facilitate the decarboxylation, right? And we have seen how that happens. So we need a cofactor that will serve as an electron sink, right? So the solution is the same that we have seen before when we were discussing pyruvate decarboxylation in alcoholic fermentation, and we use TPP. Okay, so at this point, I will let's do the reaction on the board, because I think that's just about the only way that you can understand how it happens. So we'll stop sharing this, and we will share the whiteboard. All right. All right. So let's see what we have. All right. So we have pyruvate. Let me write the full form. Okay. So, all right. So this part has to go. The way now we're going to bring in TPP. That it will do its trick. Okay, so that TPP, let's that TPP will attack this carbon. The carbonyl will open up, will pick up a proton, and we'll end up with this intermediate. We're going to have a variety of intermediates. Okay, okay. That's what the pyruvate will look like. All right, and TPP. Okay, we have our first intermediate. Now, and that's a plus here, the nitrogen. This is where the beauty of the electron sink function of TPP will come in. The CO2 now can go away because these electrons now can bounce onto TPP. Okay, so CO2 will leave. So we have a decarboxylation. All right, and we have a new intermediate here. All right, and this is really one of the forms that stabilize the carbanion, and this will go back and forth to this. There's a carbanion. So it's this ability to go back and forth between these two forms that stabilizes the carbanion. Now, the carbanion at this point will, there is lipoic acid now. It's coming into play. Lipoic acid looks like this. And it's got some extra stuff here. So lipoic acid will be attacked by the carbanion. And now we have a new intermediate. This is a very interesting intermediate, actually. It's got two cofactors on it. First, it's got TPP that I'm drawing right now. I mean, how weird is that? What's this, like this? Okay. And then it's got the lipoic acid. Okay, that's like that. It's reduced. It's become a sulfhydride. All right. Now, at the next step, TPP can go away, and it will become this. Okay. There goes TPP, and what we're left with is acetylated lipoic acid. Okay, here we forgot a carbon. All right, that's a methyl group. That's the carbon. So that's the acetyl group that's now has formed a thioester with lipoic acid. Now, if you spot where the oxidation is, the oxidation happened here, right? So the oxidation has happened. So this is what we get now. We got our CO2. That's one product. Oops. Okay, and we oxidize this carbon. This carbon now is equivalent to a carboxyl carbon, but it started out as a carbonyl carbon, right? So we have the oxidation of the carbon, and we decarboxylated pyruvate. So that's an oxidative decarboxylation. Of course, we don't see lipoic acid anywhere. In fact, what we do see is acetyl-CoA. So now in the next one, now CoA comes in. Okay, so CoA, of course, it's something big, but that's the business part. And all we have is a replacement of one thioester for another. Okay, so this is what happens now. We generate acetyl-CoA. Okay, there it is. So this is our other product. And we're left with fully reduced lipoic acid. So we got our products. Now we got, what we're looking for, which is acetyl-CoA. That can go on into the TCA cycle. Right? Are we done? No, because at this point, what we have is reduced lipoic acid. If we ask the enzyme to do it again, how we're going to make enough, we're never going to have oxidized lipoic acid to do this reaction, right? Right here. So we have to regenerate that. So this has to become, so the reduced, lipoic acid has to become oxidized again. And that is the job of the E3 enzyme. We'll see how it happens in a minute. First, the electrons are passed on from, okay, let's write this. We haven't seen this compound, but we'll see them on the slides. From FAD to give rise to FADH2. So it will reduce another electron carrier compound that we have not talked about, FADH2, and we'll see why that is. And then NAD plus will come in and pick up the electrons from FADH2, oops, to become NADH. Okay, so that's the general cycle of pyruvate dehydrogenase. We'll see in more detail these redox reactions when we go. We return now back to the slides. All right. So what I'm going to do is, hold on. Okay, I will stop sharing this screen, and we will share another screen. That will be here. Okay. All right, so we saw TPP. Let's zoom through the steps that we discussed. There is a carbanion, and it can be stabilized by TPP. That we saw this part. That's part of the E1 enzyme. Okay, and the purpose of TPP again is to serve as an electron sink. Then we have lipoic acid. So the E values will become important here. So for the half cell, going from oxidized to reduced is minus 0.29. Okay. Remember that to go from a carboxyl to go from a carbonyl even more. So it's extremely favorable. Okay, that explains the big delta G that we get. So we have minus 0.29 plus 0.5. So you have a delta E of plus 0.2 and some change. So that's a very favorable. It's a positive delta for the redox reaction if we couple this here. Let me just go back to explain this. I think I have it on a slide, but let's go back to, where's our whiteboard? There it is. So let's make another one. So this is the, okay, for if we have, if we write as a half cell, the E value here for lipoic acid, so we start with this, the half cell plus 2 electrons to go to this. So that's minus 0.29 volts. And if you want to go now as a reduction, writing the carbonyl, so the carboxyl, sorry, that's the equivalent to the thioester that we had seen. That will be, minus 0.5, okay, volts. So the delta E, we write whatever gets reduced, which is the top reaction here, okay. Here. So that will be minus 0.29 minus 0.25. So that will be, about 200 or something, one plus 0.21. Yes, so that's a plus. So it's a plus, so it's thermodynamically favorable, and the delta is actually quite substantial. All right, so that's all good. That's all good, but now we need to regenerate. Let's go stop there and go back to the other one. We have to regenerate the oxidized form of lipoic acid. Here, this is the mechanism we have discussed. Okay, that's the oxidation step of the carbon. And in part 2, again, this is where we have acetyl-CoA being forming, and we end up with this, the reduced dihydrolipoamide. All right, so why do we need 3? This is the tricky part. E3 comes in to restore it to its original form, right? And I just described that, the value of that. So NAD plus now has a minus 0.32. If we try to couple this reduction with this oxidation, we have minus 0.32, okay? Minus 0.32 minus 0.29, we're still with a minus. We're at the minus 0.04 or something like this. So we need something, you know, a reduction potential that has a higher value than 0.29. So that's not good. So that's why NAD is not used. So we need something that's stronger, that's more positive. So because again, remember the electrons. Let's go back. For something to be favorable, okay, whatever gets reduced has to have a higher E value than whatever gets oxidized. The rich tend to get richer, but NAD has a lower E value, so that's not very favorable. So we need something else. So if we bring, sorry, I go back. But now if we bring FAD, okay, that is definitely way more positive than the minus 2.29. Okay, it has an E value that's way more positive. So exactly how positive, it depends. It depends on protein environment. So when it's bound to something, and as a standard, it's around 0, but it can fluctuate dramatically. So at least in principle, this seems to be favorable. But then somehow we have to couple FAD to NAD, and that is also unfavorable on paper. Okay, so here we wave our our magic wand and say yes. On paper, the delta E value here seems to imply that this is not a favorable reaction. So FAD cannot reduce under normal conditions NAD plus to make it an NADH. In fact, as we will see in the electron transport chain, you go from NADH to FAD, you don't go backwards. So this is an exception. Okay, whatever happens at the E3 enzyme, I don't know what chemical environment the enzyme generates. I have tried to find it how it can be rationalized, but it cannot. Okay, so everybody presumes that there is something special in the microenvironment of the E3 enzyme that makes this thermodynamically feasible. Okay, but that's what we have. So we have NAD actually picking up the electrons and giving rise finally to NADH. And again, the hand waving explanation is that the protein environment has probably changed the reduction potential. So this is actually the only case that we'll do in class that we have something that seems to be unfavorable. Okay. All right, and that's the overall scheme. So it's this last part that seems to be unfavorable. Everything else makes sense. The oxidation of the carbon by lipoic acid makes sense. We explained it with the delta A. We saw all the intermediates, how it's formed. The oxidation of the reduced lipoic acid by FADH makes sense thermodynamically. The last one here doesn't, okay? And we have to invoke some magic protein environment. And coupling to super favorable reactions up here too. All right, so we have E1, E2, and E3. What's important about the E2 part is lipoic acid, okay? This is a key cofactor, but it's not the only one. I mean, the pyruvate dehydrogenase complex has many cofactors. So we've seen 3 distinct enzymatic activities, E1, E2, E3. There are 5 vitamins. There is thiamine, which is TPP. We'll talk about FAD in a minute. It's riboflavin. NAD is called niacin, and pantothenate is a coenzyme A, and we have seen lipoic acid. If you go on to any health food section of your local grocery store or any more specialized stores, you will find all of them in vials. Presumably, you take them in your diet and you become you have superpowers. But this is again a giant enzyme with 5 distinct vitamins and cofactors. So FAD. Now, why is that? Each one, let's see. TPP is electron sick, helps in the decarboxylation. riboflavin and niacin is in E3 to help reduce their electron carriers, and they helps to oxidize, lipoic acid. Riboflavin looks like this. We have not seen it. We've seen NAD and NADP, but not riboflavin. So it starts like this, and the actual FAD8, the reduced form, looks it's a little more complicated. And again, you see these vestiges of a nucleotide here. Actually, it's a real nucleotide, and which are vestiges probably of an ancient RNA world. So the electron, but the electron carrier proteins are up here. Okay, not on this part. And they're actually very interesting. It picks up FAD in this reaction we just discussed. It can pick up 2 electrons, and it's got this ring system here that you can easily bounce electrons around of the nitrogens here, as you see. But it does something that NAD does not. Okay, it can also take single electrons, not just as a pair. Remember, NAD and NADP pick up the proton as a hydride with its 2 electrons always. Okay, it never picks up one electron and 1 proton. But here, FAD can do this. It can change the current essentially from 2 electrons to 1. They are really the electric transformers of the cell, so it can do that. Coenzyme A, we have briefly mentioned before. Again, you see the same parts as in others, the vestiges of the RNA world. The business part is right here. So it's a universal carrier of activated 2 carbon units in all cells. Very ancient metabolite. That's coenzyme A. Yes. And remember again that forming or hydrolyzing this thioester coenzyme A releases an enormous amount of energy, as we had discussed previously. That it's a very high energy thioester bond. Okay. And because unlike the oxygen esters, which in those you can still delocalize the negative charge on the carboxyl carbon, that option is not available on the thioester. So the thioester has a very high energy. All right, lastly, we've seen lipoic acid. It is an electron carrier. It participates, that's actually what participated in the oxidation of the carbon, but of pyruvate, of carbon 2 of pyruvate. So it is an electron carrier, but it has also a structural feature that makes it extremely useful. It has a very long arm and can bridge the different subunits on the enzyme, right? So the enzyme, this is E2, which has the lipoic acid, and can really swing, from one to the other, and that is pretty much it's a very important function. It makes it very, very valuable to the cell. All right, so and the E3, it has to reach also the E3, which will oxidize the sulfhydryls to regenerate the oxidized form of lipoic acid. So that is the summary of the pyruvate dehydrogenase complex. And that concludes this video, and we'll continue with the next one of how actually the 2 carbons finally make it into the TCA cycle. So we'll stop here.